Hello! In this new series, we will explore physics programming in depth, starting with integration methods. Integration is the mathematical operation that accumulates change over time. In physics simulation, it allows us to advance the state of objects from one moment to the next. Integration allows us to derive velocity from acceleration and position from velocity. Integrators are numerical methods used to approximate the ordinary differential equations that arise from Newton's second law. Force equals mass times acceleration. An ordinary differential equation, or ODE for short, is an equation that involves derivatives with respect to a single independent variable, which in our context is time. All integrators are approximations of these ODEs, and therefore introduce numerical error. This error arises for three main reasons. 1. They use discrete time steps to approximate motion that is actually continuous. This causes curved trajectories to be approximated with straight segments over each time step. It is analogous to representing a curved surface with a polygonal mesh. 2. They use floating point types, which have finite precision, meaning most real numbers cannot be represented exactly. So operations are rounded to the closest representation. These small rounding errors accumulate over many integration steps, particularly when delta time is very small and the number of steps becomes large. 3. Taylor series truncation, which I will now explain. The Taylor series is an infinite series of summation terms used to approximate the output of smooth mathematical functions. The Taylor series has its form because it is the unique polynomial that matches a function and all its derivatives at a point. The factorial terms arise from the repeated differentiation of powers of the expansion variable. The expansion point is the point along the x-axis where we choose to approximate the function. The first term is a constant value at the expansion point. The second term is a linear value that roughly approximates the direction of the function at the expansion point and is tangent to the function at that point. The third term is the quadratic value that approximates the curvature of the function in the local region of the expansion point. Each additional term uses a higher order derivative of the original function, improving the local approximation and expanding its reach. A first-order integrator, such as forward Euler, matches the Taylor series up to the linear term. Each successive Taylor term uses a higher power of the time step. When the time step is a fraction less than 1, squaring it makes it smaller, cubing it makes it smaller still, and so on. Because of this rapid shrinkage, the first term we leave out is the largest source of error. The lack of higher order terms present in an integrator is Taylor series truncation error. As the time step approaches 0, the truncation error decreases because each step deviates less from the curvature captured by the missing higher order terms. Aside from these three sources of numerical error, the differential equations we approximate are themselves idealized models of reality. They assume perfectly rigid bodies, continuous forces, and simplified interactions. So even with infinite computational precision, a gap between simulation and real-world behavior would still remain. Since local error is the curvature we did not compute within an update step, global error is the accumulation of these unmodeled curvatures over the course of the simulation. For a first-order method such as forward Euler, the local truncation error scales with delta time squared, because that is the first missing Taylor series term. However, because the number of steps required to simulate a fixed interval of time increases as delta time decreases, the accumulated global error scales approximately with just delta time. There are three types of integrators: explicit, implicit, and semi-implicit. The latter are also called symplectic. These categories are not necessarily mutually exclusive. An integrator can be explicit and symplectic, or implicit and symplectic, but it can't be explicit and implicit simultaneously. Explicit integrators compute the next state from the current state without requiring solutions for unknown values, making them computationally cheaper than implicit methods. Examples of explicit integrators include Runge-Kutta 2, Runge-Kutta 4, forward Euler, and Verlet. While higher-order methods like Runge-Kutta sample the trajectory at multiple points within the time step to improve accuracy, they can still become unstable with large time steps or stiff systems leading to energy growth. Regarding forward Euler, if we were damping the speed of an entity with an initial velocity of 1, a drag coefficient of 0.9, and a delta time of 2.23, the magnitude of the velocity would be 1.007 after the first update. The magnitude of the velocity has increased despite the drag coefficient being below 1. If we now set the delta time to 2.2, the magnitude becomes 0.998, and subsequent steps will converge towards 0. For forward Euler applied to a linear decay system, such as the application of air drag, if the product of the decay rate and delta time exceeds 2, the system becomes unstable and begins to grow exponentially. If it is exactly 2, the system oscillates without converging or diverging. Forward Euler grows energetically in energy-conserving systems, such as an undamped spring or planetary orbits. It updates position using the old velocity, so each step is based on outdated information and overshoots the true path. For example, in a spring system, it uses the previous velocity to advance position even as the spring begins to recoil, causing the position to advance too far before the correction is applied. This is reflected in the energy equation, where each update multiplies the energy by a factor greater than 1, leading to systematic energy growth. Implicit integrators are more expensive than explicit integrators because they force you to solve algebraic equations at each time step. Examples include backward Euler, implicit midpoint, and implicit Newmark. They are called implicit because the unknown future state appears on both sides of the update equation. The first equation you see describes how drag is incorporated into the velocity for forward Euler, an explicit method, and the second describes how drag is incorporated into the velocity for backward Euler, an implicit method. Notice how the future velocity state is on both sides of the equation for backward Euler. To solve the implicit equation, we bring all terms with the future velocity to one side. We factor out the future velocity, then we solve for it. If we assume the drag coefficient is positive, then the denominator is always greater than 1, so no matter how large delta time becomes, the new velocity is never larger than the previous one. This makes implicit integration more stable for a wider range of delta times than explicit methods. They are widely used in cloth, soft bodies, and constraints because of this tolerance. Looking at the backward Euler algorithm, we can see that it updates position using the updated velocity rather than the old one, unlike forward Euler. This velocity already includes the effect of the restoring force, so the motion is corrected before the position is advanced. In this example, that dependence on the future state appears as the denominator when the algebraic equations are solved. Whilst forward Euler applies the new acceleration too late, backward Euler applies it before the step is taken, causing the energy to be overly dampened in energy-conserving systems such as planetary orbits. The energy equation for backward Euler is as follows. The third type of integrators are called semi-implicit, which are also known as symplectic integrators. The term semi-implicit is misleading, as these methods are not a midpoint between explicit and implicit integrators. They keep the total energy bounded over long simulation durations. The energy does not continuously drift upward like forward Euler or downward like backward Euler in conservative systems. They are typically favored in physics engines because of this attribute. They obey the geometric structure of Hamiltonian mechanics, which preserves how energy flows between potential and kinetic components. Symplectic Euler, Verlet, and leapfrog are examples. Looking at the algorithm, we can see that it first updates the velocity using the current acceleration, and then uses this updated velocity to update the position. This means each step incorporates the effect of the restoring force before advancing, so the motion neither consistently overshoots nor undershoots the true path. For example, in a spring system, the velocity is reduced as the spring begins to recoil, and this corrected velocity is then used to update the position. Because the correction is applied before the position update, the motion remains balanced rather than drifting outward or collapsing inward. The energy equation for symplectic Euler is the following. Notice that it does not multiply or divide the previously calculated energy, like forward and backward Euler. It instead depends on a mixture of velocity and position terms, which represent kinetic and potential energy respectively. Because of this coupling, the error does not accumulate in one direction, but instead oscillates over time. Thanks for watching.